And so this is a quick go over all of experimental techniques, topic 1. So we know we have 3 states of matter: solid, liquid, gas. This is grade 3 material. What grade 3? KG2. So we have solid, liquid, and mass, and we know that all matter is made out of atoms, which are tiny particles, cannot be seen by the naked eye, baby stuff. And when we change state of matter, you're adding or removing energy from the one the particles already have. And that's this part. Now, we know that. Now, solids, these are how they look like. Liquids, gases. This part, I'm not really going to go over it much. Just know that solids and liquids cannot be compressed while gases can. I feel like they're going to ask something about that. And the forces, stronger than liquid, not as strong as solid, and non-existent. So this, just go over it in your own time. It's literally, we've been taking it for years. Changes of states. I will be worried if you don't know them. Now for this part, here's what I do usually. You write down on your piece of paper solid, liquid, gas. From solid to liquid to gas in this way, it's endo. And now going from gases to solids is exo. This is how I memorize it. Now memorize this small thing. Khalas, you have the entire, this part of the exam memorized, the melting, whatever. Now kinetic theory, it just tells you that everything is made out of small particles that are in constant motion and they're invisible. And the lighter it is, the faster it moves. And when you increase temperature, they'll move faster. Logic. Now Brownian motion is the motion in fluids that they move randomly because they are bombarded by other moving particles in the fluid, which means like the other liquid molecules. They're light and fast moving, and they're named behind Robert Brown when he saw pollen grains but didn't decide, like he didn't actually figure it out until Einstein did later on with water molecules, and this was the evidence for the particle theory. This is not important. I highly doubt they're going to bring anything about it. Now, diffusion, it's just to fill up the space available for them in gases and liquids. Now, experiment 1, if you diffuse bromine. Now, when you remove the cover between them, particles are going to start moving around and mixing. Now, we know that they're going to remain continuous movement, and it's higher concentration to lower concentration. It's going to go always. Now, when they're fully mixed, no more color change is going to happen. You're just going to have this one shade of brown that's not going to change. But their movement will continue, but it will be at equilibrium almost. And here, formation of ammonium chloride, it just tells you that... So just tells you that a white ring of ammonium chloride is going to form closer to the hydrochloric acid ring. And it's because hydrochloric acid is lighter, or is it heavier? It's heavier. If it's closer to it, then it's heavier than ammonium. By the way, you could just see this on a periodic table and calculate it yourself to know which one's heavier. But anyways, so the gas particles move at speed of 700 meters and random motion. So see, ammonia is lighter and then hydrogen chloride. So they move faster, so that's why it's closer to hydrogen chloride. Now in liquids, it's way slower than in gases. We need to know that. I'm gonna go back to the reading position. Now, these, I'm very sure they're not going to bring much about them. But really quickly, molecules of water, they'll collide with the solid, they'll dissolve them, and they're spread out by movement of molecules, and it's the same thing, it's diffusion. So when we have studying chemistry, we need a lot of things. We need measurements. Our measurements could be time. Time is usually with a digital stopwatch and to 2 decimal places. We have temperature. It should be to the smallest division and in time. And usually at with a thermometer. Mass with a balance, top pan balance. Volume, volumetric pipettes, measuring cylinders, depends on the accuracy you need. Burette, very accurate up to 50 centimeter cubed. And a burette can be used to measure the volume of a gas. A gas? No, it's a liquid. Guys, I'm honestly not sure about this. I think it should be a liquid, not a gas. Because I've never seen a burette to measure gases, to be fair. Anyways. Okay, they all... Yeah, I think this is wrong, guys. Anyways, pipettes used to measure accurate volume of liquids. And common capacities are 5, 10, 25, 50. Guys, I don't know if you remember, this was a question that they used to bring last year, because we had this chapter last year. So memorize them, 5, 10, 25, 50. And cannot be used to measure a volume of a gas. As it's not graduated, it has one calibration mark. That's why maybe they said that you could use it with a gas here. I'm not sure, to be honest. Measuring cylinder, approximate. It's not that accurate. And can be used to measure the volume of a gas. So guys, I think burette can be used to measure volume of gas. And I'm just mistaken. Volume of gases, most accurately, gas syringe. Can be used by a gas jar, but it cannot make it as accurate as the graduated measuring, or it can be as accurate. A gas jar cannot measure the volume of a gas as it's not graduated like a measuring cylinder. Okay. And this is how it would go. Delivery tube and gas jar, and water. Anyways, pH, we just talked about it in chapter 3. Reliability, you need to have it reliable information, repeatable, so that when you repeat it again, you're gonna get really similar results, and reproducible, that different people will do this. Yeah, like I said, that no matter how many times you do it at the same conditions, you're gonna get similar results. So to make sure it's repeatable and reproducible, the variables need to be studied, and you need to see the collected variables, which are controlled variables, which is anything that stays the same during the whole experiment. Independent, which is anything that is changed, and they're usually plotted or always plotted on x-axis. And dependent variable is anything measured during an experiment, and it's always plotted on the y-axis. Now, when you have the different types of errors, you could have a random error, which is human error. Systematic error is anything wrong with the things you're using to make the experiments. Anomalous, or anything unusual or unexpected, like getting a measurement way too high or way too low. A zero error is when you have an instrument, let's say like when your balance or your thing you're measuring mass with isn't calibrated to the 0 point, like without anything on it, it measures, let's say, 2 grams, which it shouldn't. It should be at 0. So this is what a zero error is. When you're plotting, graph plotting, guys, just read this. Independent with dependent, scales as large as possible, label axes, give your graphs titles, use a cross. Oh yeah, this is use a cross, not a dot. This is because using a sharp pencil. Be careful, because this is for accuracy. Like, this is more accurate than this, because you can make your dot as big as you want, covering as much space as you want. Whereas this is measuring this point exactly. Like, see? This would be the point you actually need. That's why you use a cross. Draw the line best fit. Try to make it pass through all the points. Try. Don't have to. Yeah. Do I really need to explain this? Atom, smallest thing, like this. Element is a pure substance which is made out of one type of atom. Compound is a substance that is made out of 2 or more type of atoms, or well, elements, sorry, not atoms. Compounds made of different elements, and it cannot be separated by physical methods. A mixture is a different group of elements or compounds that are not chemically bonded. Read them really quickly, don't just stay on mine. Define an element, a compound, and a mixture. This is really easy. We just read them. I think blood's a mixture, oxygen is an element, ammonia is a compound, orange juice is a mixture. I'm not sure about blood, but I'm assuming it's a mixture. Solvent, solute, solution, saturated, residue, filtrate. Words to remember. So guys, remember them. Now, separation techniques. This is the most important part of this entire topic. So, read this part, it's not really important. Now, first one, filtration. Used to separate insoluble solid from a mixture. Insoluble from a mixture, like sand and water. Yeah. The filtrate is whatever is going down here. This is a filtrate, and this, whatever is left in here, is a residue. This is your filter funnel. Inside that you have filter paper, and this is your conical flask. We took all these experiments last year, so you should all know them. Suitable solvent. What this means is, let's say you have a mixture of salt and sugar. Salt, sugar, or well, let's make sugar blue for fun. Sugar. Let's say. Now we know that sugar dissolves in alcohol, but salt doesn't. So what we're gonna do is we're gonna pour alcohol and dissolve all our sugar. So you'll be left with solution here with, this has A and S, I'm gonna say, and you're gonna be left with salt, undissolved, by the way. So once you do this, you're gonna filter out. You're gonna take your same experiment thing. This is your conical, okay, that's the worst thing I've ever done in my life. You're gonna take your conical flask with your filter, whatever, with the filter paper. Here you're gonna be left with the salt, and here you're gonna be left with the sugar and the alcohol, but we don't care, so sugar, here with salt. And then later we could, evaporate all the liquid. So with the sugar, just put it over fire. This is supposed to be fire, in a bowl, until all the water evaporates and you're left with sugar in the bowl, because we don't need the alcohol here. And that's it. Crystallization, we should all know this. You're gonna first heat until most liquid evaporates, then you're gonna put it over a steam bath until the crystallization point. Which, by the way, is the point where, by the way, you could check it by getting a cold glass rod and putting it in. If you put it in and it forms crystals around the glass rod, you have reached crystallization point. Then you're gonna leave it to cool, you're gonna filter out crystals, and you're gonna dry them or leave them in open air by filter paper or open air. Now, okay, so briefly describe how separating mixture of salt and sand by dissolving the salt in water and filtering it. This question, I don't know why I didn't solve it, but sure. Give the name of an apparatus or the name of a technique. A mixture of sulfur and steel. So this one is a gas and steel. Yeah, honestly, I don't know this question. Cooking oil and water. This one we could use separatory funnel. This one, yeah, I'm not gonna try to think about it. Obtain large crystals. The minute you see the word crystals, it's crystallization, and then you conduct it by this. Separating funnel. Two non-dissolvable liquid or non-mixing liquids. You're gonna put them in your funnel like this. The denser one is gonna go to the bottom, less dense is gonna go up. Then you're just gonna let the denser one go into another bottle, and then you're gonna release the less dense one. It's really easy. Read them all these. I'm explaining really quickly. Just read them over them when you're done. Simple distillation, pure liquid form, let's say you have salt water. This is how you filter out the salt and the water. This, you do it when you want the water alone and you want the salt. If let's say you wanted the salt without the water, you crystallize it. But if you want the salt and the water, this is what you do. You heat it until the liquid with the lowest boiling point evaporates, or boils. It's gonna travel up into the condenser. Then it condenses on the cold surface, and the liquid's gonna go into collection flask. And we know that the water is going in from this point here, closer to the, see? From here, water is going in. From here, water is going out. Or well, not like this, the arrow. Like this. So, and then what you collect is called distillate, and what's left here is called residue. So what you're doing practically is by heating it, you're gonna make it evaporate, and then it's gonna condense and go down again. What you could use to simple distillation, sodium bromide, aqueous solution. You could use this for all aqueous solutions, I think. And what sugar and water solution. Like I said, or well, salt and water, anything, doesn't matter. Fractional distillation is when you have two substances with really, really close boiling points. The only difference is the exact same thing, except you have this thing called the fractionating column. It's filled with glass beads, and it's gonna hold on to molecules and drop them again so they don't mix. Now, these things aren't the most accurate. You're not gonna always separate 100%, but they're the closest you can get to separated. So like your distillate will be the most volatile, or like the one that has the lower boiling point usually. So ethanol and water, since they have close boiling points, and any mixture of miscible liquids that have a close boiling point. Paper chromatography. Okay, chromatography is the mixture dissolved in a fluid and stationary. Okay, this doesn't really make any sense or matter. Paper chromatography. I think we're almost done with this all. Yeah, these are all experiments and things. I solved them all, I think, yeah. But we're almost done. Paper chromatography is when you have ink or a dye or chlorophyll or food coloring, and you want to see what are the components of it. You could use it for amino acids also. So let's put, yeah, it's used in the food industry and forensic sciences. Guys, we all took this. Already took this, okay. So you're gonna put it on a filter paper, like here on a dot. This is your stationary phase. Then you're gonna draw a line with pencil over here where I drew the blue line. It has to be with pencil so it doesn't mix. Then you're gonna put it in a solvent that it is soluble in. It could be water or alcohol or both. And now it's gonna start moving up. Okay? By the way, if it's alcohol, you cover it so it doesn't, because alcohol is volatile, which means it evaporates readily at room temperature. So yeah. Now it's gonna go into capillary action, which means it rises up. And when it reaches somewhere over here, you stop, you remove it. Okay? And the paper would be called a chromatograph. Okay, so now when you draw, yeah. So what happens when it's going up is each component has a different, components have different solubilities in the solvents. And they'll adhere to the paper differently. And they'll travel different distances of the paper. The component that is most soluble adheres the least, and it will travel the longest distance. So the least, the soluble, it's gonna go the highest. And the more soluble, the lowest, like shorter. And that's everything. And when you want to find, let's say, RF for red, you're gonna do distance A over distance total, or well, distance B. So yeah, chromatography. Okay, so sometimes when you have the colorless or like amino acids, it's gonna be sprayed with a locked-in agent, which interacts with the components, making them colored, so they're visible. RF is a retention factor. It's a value, and yeah, it's measured. So it's distance traveled by substance over distance traveled by solvent. And it's a physical property, and each substance has a unique RF value. Okay, so how can you interpret this chromatograph? Let's see. If we know substance 1 and substance 2 and substance, let's see, what other substance do we have? 4 are pure substances. Why? Because when you draw a line, you're only gonna find one singular point on those lines, and they did not split. Now 3, 5, and 6 are not, because look, 3, it's split into 2 different points, one here, one here. 5 is split into also 2 different points, one here, one here. 6, 2 different points, one here and one here. So since they split and they have different RF values, they're not pure. Now we know that 2 and 5, since they're at the same horizontal level, they have common components. Same with 5 and 3. Same with 4 and 6. Or well, no, sorry, 3 and 6. Not 4. 4 is, yeah. They have a common value because they have the same RF factor for some of them. If the substance does not move up and it remains at the baseline, which means here, it's insoluble in the solvent. You need to pick a solvent that's soluble, okay? Here it's a question. What's the least affinity, has the least affinity to the paper, which means which one is the least soluble, or I mean the most soluble, which means it's gonna go up highest, which is A. RF, you're just gonna do here 8 over 12. 8 over 12 equals 0.67. That's it. Now, if you have amino acids that are colorless and you want to separate them, you could expose it to UV rays to reveal spots, and it could be sprayed with a locked-in agent, which forms different colors with different amino acids. Okay, so now this one. Purity of solids and liquids. Solids and liquids. The best way to check for solids is melting point, liquids is boiling point. And these are your physical constants, which means for the same substance, like water, you will never find pure water that does not boil at 100 degrees Celsius. Easy. You will never find this. And you will never, ever find water that's pure and does not freeze at exactly 0 degrees Celsius. And if they do not do at exactly these numbers, they are not pure. That's it. See? Pure water at 100 degrees Celsius. But when you mix it with water, with salt, 102. And for colored dyes, we said we could use chromatography to see if it's only one point that does not split or many that split, to see purity. Okay, so colorless liquids, and it told you it's water by testing melting and boiling points or any physical constant like density and whatever. Purification of impure solids. Dissolve it in which it's solvable, or filter it and evaporate it, solution into crystals. Impure liquids, simple distillation, fractional distillation. Memorize it. Working with gases. How do you collect gases? Any gas could be collected with a gas syringe. Gases less dense than air, upward delivery. Our examples are hydrogen and ammonia. Gases denser than air, downward delivery. Chlorine, sulfur, hydrogen sulfide, nitrogen, carbon dioxide, hydrogen chloride. Either you memorize them or you memorize the density of air and calculate it during the exam. One of the two. Preferably memorize. Gases collected over water must be insoluble in water. Oxygen, hydrogen, nitrogen. Usually. Now, drying of gases, you could use a drying reagent, or for solids, and as a solid you use anhydrous calcium chloride. A liquid one would be concentrated sulfuric acid. Now, toxic gases like chlorine should not be prepared in a fume cupboard. Okay? Okay. Nor pollutant gases like nitrogen dioxide. Concentrated sulfuric acid is never to be used with dry ammonia gas because it's basic and they will react together. So concentrated sulfuric acid, you will always dry it with, sorry, I meant ammonia gas. You will never dry it using sulfuric acid. Always ammonia gas, dry it with calcium oxide solid, which is this one, the first one. Now, calculate the molecular masses of both these and compare their densities under identical concentrations. So I calculated this one to be 834 and this one to be 17. So if this one's gram, or like measure of mass, then this one is usually like 2 over like 2 to 1 density of that one. That's like, yeah. So since I think so look, for these two gases, I think the constant for air is 22 point something. I'm not sure of it, so it's 22, but I don't know 22 point what. So if it's more than 22, it's denser and it's going to be used during downward, and if it's less dense and upward delivery. The drying reagents, we just said them. 3 gases that are highly soluble in water: NH3, HCl, and SO2. We have them written somewhere up. And a label diagram. Yeah, I didn't draw anything. If you want, open the CQTs and see it. Okay, this question, did I solve it? Yeah. So which of the following are R and T most likely gonna be? What you do is just 8.2 divided by 14. Okay? And then you're gonna get what R is, which you're gonna find it to be when you compare it to valine. And T is 6.16 over 14 proline. You're gonna find them to be. So A, B, C. A is a separatory funnel, B is a delivering tube, and C is a glass jar. Now, why did the student make a mistake? Because SO2, because he's collecting sulfur dioxide. SO2 is denser than air, and you cannot use this for it because it's gonna go down since it's denser. So it can be used by downward delivery, not upward. So what you have to do is just flip the glass jar. But a gas that could be used by this apparatus is anything lighter than air, which is hydrogen. Now, again, the student's investigating the rate of the reactions between hydrochloric acid and calcium carbonate. He's using a gas syringe to collect and measure the amounts of gases released. Okay, this question, really easy. Really easy. You're gonna just see what part of this is white or not gas, filled with gas. This here is 0. This is 30, 45, 46. Be careful, count. This is 60 or 58. This is exactly 65. This is exactly 70. This is exactly 70. And there's one more that's also exactly 70. See? Plot your points on a graph. I know it's hard. I know it's really precise and whatever. See? This is how precise I had to get to draw it with a tablet. So, guys, it's really hard to draw, but we'll be fine in the exam because they won't bring something this precise ever. So you're using the graph and deducing the volume. This question, you could solve it. An error that would be that it's inaccurate, maybe. How would you fix it? You'd use a... Oh yeah, by the way, this is when they told you that you used a 50 centimeter measuring cylinder filled with water. It's inaccurate because you need a bigger measuring cylinder. And... okay. I don't know where I got 35 from, but sure. Calculate the volume between these seconds. I calculated it. I got it to be 0.39. Do it yourself. You're gonna get this answer. This part, I totally skipped it because I was sick and tired of it. Sketch on the same graph. Okay. If I were to sketch on the same graph, it would be the same thing, but it's just gonna be steeper and ending higher because hydrochloric acid is a limiting reagent. Okay. Now let's go back. I don't need the pointer. If the gas was to be hydrogen rather than carbon dioxide, would it have been possible? No. Because hydrogen, you cannot collect it over water. Oh wait, would it have been possible? I think yes, because hydrogen is insoluble in water. So yes, and that's it for experimental techniques. Now guys, a lot of people are asking me what do they study. Here's what I would study. Chapter 1, go over the video notes I made and go over the notes made by the school. Solve the required CQDs that are written on your material paper. For chapter 2, memorize notes. And solve past papers given in the notes. For chapter 3, I posted a summary video a few minutes ago. I don't know if it posted yet or not, but if you want to watch that, do notes. Don't do soil preparation, okay? So notes and just do CQDs if you can. I would do the quiz 3.1 and 3.2 because they are with us. 3.5, not sure. I would do also AMS quiz, and AMS quiz contains topics and whatever, like topics mostly, and chapter 3. So that's what I would study. And yeah, I'm done. Hope you have a nice day. Bye.